going to start by the HIL side of all our FPGA solution. So basically, this solution is made to test ECUs. What is an ECU? An ECU is an electrical control unit. That's the controller you got in hybrid cars that is used to control the motors and the engine. And what we provide is an HIL system, so that will emulate the plant behavior in order to perform a lot of tests on the ECU part. So my presentation will start by describing what is Hardware-in-the-Loop solution, what is the objective of those solutions, what are the challenges we need to respond. Then I'm going to introduce very quickly our FEA partners, why we use FPGA. Then I'm going to describe the OPAL-RT eFPGAsim solution for HIL application. And finally, I'll close the loop with our DSP board, the OP-8665. So here is the development process of a controller. So you start by a desktop simulation. Then after, you do rapid control prototyping. So you have a real plant, maybe reduced, maybe not the same as the final one, but you'll have a real plant with a simulated solution for the controller. When you made that, you code your controller, and when you got the controller code, you go on the HIL system to test your controller code before getting to the bench. So here is the part where OPAL-RT can help you. Hardware-in-the-Loop or rapid control prototyping. Hardware-in-the-Loop. So we got an ECU, a controller, connected to a real plant, and what we're going to do, we're going to substitute the real plant by a virtual plant. And the main difference will be at the level of the signal integration. They are not the same signal. Before it was the analog world, now it's the digital world. So there is some consideration we need to make. So what we want to do is to detect ECU code bugs earlier in the process. We don't want to come to the real bench and have this kind of problem. So this is not accepted by most companies, that you completely destroy your bench. So this is why we got HIL, is to avoid this kind of condition. And what you want to do too is to increase the test coverage. Because on a real bench, you won't do all the tests you can. You'll do only a small part of it because it costs a lot to operate, and it can be also a lot of cost to maintain it. But one of the real reasons, and the reason why we sell a lot of HIL, is because we need to get more efficient to develop this kind of technologies, the ECU technologies. So we need a development loop that is smaller and smaller. So, and we need also to reduce the dyno usage. And your boss approved this kind of idea, less you get to work on a project, less it's cost. So this is why this HIL is now part of the process, of the development process. Now, when we think about a simulator, we think, why don't we take advantage of this flexibility to make things we can't do on a real bench? And why don't we, for example, simulate things that we don't have on our real dyne? So we need also on HIL system to be able to change the plant easily. Now the challenge. The first challenge is to wire everything. Julie can tell us, she is one of the team leader in the production team, so she knows how it can be hard to wire everything. And this is why we got a lot of scalable solution, mapping boxes. And we have also software solution in order to close the loop more efficiently. Actually, my demo will be about that. You see those wires are not connected. I'm going to connect them live, okay, and run the closed loop demo. So signal connection and compatibility can be tough. So we have a lot of different drivers we can provide to emulate protocols. Integration can be hard to do too. So we provide mapping box turnkey system as this one. And also, sometimes you need a few signals, so you're gonna go for a very small chassis, and sometimes you need more. So we have a bunch of solutions that are available for a lot of different applications. Now, the second challenge is the test automation. So you want to apply fault, you want to run test scenarios, you want to use monitoring tools that make you able to define your test sequence, to run it, and then to analyze the results. And I'm going to show you that we give you the capacity of doing that. The last challenge is the model accuracy. And this is where our FEA partners comes in. It's because ECU now are very complex. They are specific to one plant, to one system. And we don't want every time to change everything because we change one little parameter. We want it to be flexible. And we know that FPGA are not that flexible. So now, because the ECU are very complex device, we need a model that fit exactly the real system. And this is why we started our collaboration with GMAG, Infoletica. GMAG, it was a few years ago. It's now maybe 5 to 10 years we work with them for FEA model. Infoletica, it's almost 2 years now. And NSYS just come up this year. So, and I want to welcome them. They're going to present after. So thank you for being here, all the three of them. And actually, with those tools, we are able to provide models that are top class for PMSM modeling application. So don't forget to stay here just after they're going to make a presentation of their own product, and they're going to show you how you can generate your netlist or design to fit in the HIL device. So now you can ask me why FPGA, because it's hard to use for non-expert, but here is the thing, that's an hardware programmable, what is an FPGA? That's a hardware reprogrammable, that can be, that's an hardware programmable device, so everything is hardware inside, just logic block that can be routed automatically together. And the FPGA means field programmable gate array. For non-expert, FPGA are tough to understand. It's like 2 hours compilation, the timing doesn't pass, the division need to be avoided, so it can be tough for non-expert to use. And our goal in OPAL-RT is to make that easier. So, last thing, why FPGA? Before, this was your system. Now you replace it by a simulator. So before it was real analog world before the TU system, but now it's digital world. And the problem with that is when you go digital, you got a lot of aliasing and latency added. And on when you use a CPU simulation, if you got 40 micro, it can make your controller unstable. So these effects are not physical effects. They cause unreal constraint on the control algorithm. And to reduce aliasing and increase the resolution, you need to increase the resolution. And if you want to reduce the latency, you need to avoid all useless digital level. And this is why we use FPGA. So basically, with the FPGA computation, you can remove a lot of those latency. Here on the top, this is the basic model we sell. It's like a CPU model. You have your model, your plant inside the target PC, and you got the controller outside that's connected through the IOs. And the problem is to go to the target PC and come back to the controller. You have the PCI Express link, you have a refresh rate that is quite high, and that can make a controller unstable. And basically what we do, we just move the model inside the FPGA. So before, the latency was 40 micro, the feedback resolution is 50 micro too. When you do this operation, you get a feedback latency of 1.5 microsecond and a feedback resolution of 1 microsecond. So that's the main interest of FPGA. That doesn't compute with better precision, it's just faster and with less latency. And it makes your controller more happy in the loop. Now, eFPGAsim. So this solution is made for smaller model, for model that with less than 30 single phase nodes. The time step are under the microsecond. The application type are for HIL testing for a smaller design. So for example, 3-phase bridge with a boost is perfectly okay for FPGA. For bigger system, it can be tough to fit in one FPGA. We got also multi-FPGA systems. So here is where eFPGAsim is located in our product line. What we want to democratize FPGA simulation. We want you never to recompile the chip, never to spend 2 hours, useless hours to compile it, never reflash you. This is the product's mission. Now, this is our base solution on FPGA. So this is an hybrid vehicle motor drive. And what we provide, we provide a model that is able to simulate 3-phase 2-level inverter with a boost converter and a motor that's capable of FEA simulation. So it's compatible with GMAG-RT, motor sold from Infoletica, and Maxwell from ANSYS. Sorry. We got a bunch of hardware function to be able to integrate easily the model in the loop. So the workflow from MotorSolve, GMAG, and Maxwell is basically the same. You have to generate a netlist file that will be assigned in the GUI, and we got the 3 options in the GUI. And after you made that, you just have to click OK. You load the model, and that's OK. Everything goes inside the FPGA. It's like almost instantaneous. Those table will fit in the FPGA, so you have the torque at the top left, the flux, then the inductance tables. And the results are shown there. So you see the phase current on the left. We got 2 different ways of simulating it. So the first way here with the harmonics is like the FEA approach. And you can compare it to the standard DQ approach where you don't have those harmonics. So that's one effect you see with FEA model you don't have on the basic model of a PMSM motor. And what's really cool about that too is the sub-microsecond time step and latency. Here you see the gate happen, less than 1 or 2 microseconds you have the result on the voltage, and same thing for the current. So it's a very high precision solver. Our roadmap for the motor model is to, so for now we support only FEA PMSM 3-phase model, Y-connected. And the DQ PMSM 3-phase, we have some textbook model, SRM models too, and a textbook model of an induction machine. But the roadmap is to add the support of new motor topologies and add the support of the temperature simulation, add the support of the iron losses. So that's our roadmap, let's say, for the next year. So now what's really interesting in that solution is because we integrated so many of those systems now, we got a better idea of what you need as an integration engineer, what you need to integrate your system fast and efficiently. So we provide a lot of tools to map your I/O and to get things easier. So I'm going to show you that in the demo. So I'm going to change. Oh, okay. Here we go. One of the features of this model is you can insert fault on all IGBTs, and you can open the phases of the motor if you want. So if you want to do some fault insertion, it's pretty easy to do here. The last thing I want to talk about for eFPGAsim solution is EHS. Obviously, that's a big part of our product, and Sergio will make a small presentation later today about this product. So I think it's at 4 p.m. something. So at 4 p.m. Sergio will make you a presentation about EHS. It's basically that's a solver on the FPGA that can be reconfigured with a netlist. So you don't have to recompile a bitstream if you want to change the topology of the electronical circuit you want to simulate. It's pretty efficient to use, and I really advise you to stay and to listen to Sergio's presentation. It's a very interesting product. Now, eFPGAsim solution answer to a lot of to all the challenges you need to I mean, it answers to all the things you need to have for a good integration of a EL system on site. So it has a very high resolution simulation because the model is embedded in a FPGA chip. Now the model precision is very high too because we use the FEA modeling approach. We have also a lot of expertise on power electronics, as you saw with Marc Langevin just before. The flexibility of this solution has been improved. So we are going to the non-flashing technology, never flash, never regenerate the FPGA code. We have a lot of smart integration function, and 3 of the leader in FEA modeling are not supporting our tools. As an endline, we can do fault, which you can't do with CPU simulation. Here with FPGA simulation, you can't apply fault. So for the demo, I'm going to use OPAL-RT DSP solution, which is an OP8665. The release date is not determined yet, but I got a prototype. I'm lucky. Maybe Julien, you want to present your product actually. Yeah. Anyway, if you have any question about this product, just see Julien is over there, and he gonna answer to that. Yeah, it's you want to talk about it? Yeah, sure, come. Yeah, it's like a party.
With microphone too. Don't worry, I won't sing. I'm a terrible singer. When I sing in the shower, actually, it's the flow stops. So. Okay. So bottom line, we had a requirement to just build a platform for education and low cost. So what we did is, well, we said, well, you know, it'd be nice to be able to configure the a controller, whatever controller you want to use, and hook it up to our simulator. So what you see here, you have like the HIL has input and outputs. And they go to this breakout box, basically, and excuse me, don't want any wires. So on this picture there, you see the TI, Texas Instrument controller, and this board can be designed for anything, for Freescale, Infineon, doesn't matter which controller you have. So, and on the board itself, we have jumpers, screw terminals, probes, probing area where you can go and put a scope. You have access to CAN, UART, serial port. So that's basically what it is. And all you have to do is provide 12 volt. And the board can be designed by us for the controller part, or the customer could have their own, and they could design it and do their testing, flashing, everything from there. Right now we have a JTAG to flash it. JTAG is just a protocol to flash microcontroller, and I guess that's about it, right? Anything else? Okay, great. Well, thanks. Yeah, you have a question? Yeah, it is. I mean, this we made two prototypes. There's some minor changes to it, but at the end of the day, it's a product. So.
So we have our own control board and interface board and laptop. Are we taking this?
Well, it depends on how big it is. At some point, this is more like for development platform, for doing your controller. But if you have a production controller, I don't know if I would advise to use that, because it's going to be normally big and packaged, right? But if you're starting from scratch, a new program, and you have a new controller, and you want to just start developing your software, and usually you're going to go through different revision of your hardware. But to get started, let's say you don't know, Freescale, TI, all these other companies, you don't know what you want to use, and you want to try it out, well, you can put it on there and evaluate what you're going to use, and also as a training purpose. So, yeah.
What is the
It's basically, it's pretty dumb. It doesn't do much. Basically, all it does is an enabler to actually have access to see all the signals. It's just like wires on a PCB, and it's a tool so that you don't necessarily have like something that you cannot put on the desk, and there's wire all over the place, and like right now where I'm almost tripping, So this is clean, it's nice, you plug it in, and you don't have to worry about, oh, which wire am I going to probe? It's all identified. You come with a scope, you can look at it, and you could also decide, you know what, I take that little TI module, take it out, and let's say I have another platform with the inverter on it, put it on there and run on a real motor. So you tested everything, and then you go, and you can go and test it. So you don't spend dyno time breaking the dyno like we saw. So that's some benefit.
Okay. So thank you. The brain. Thank you, Julian. It wasn't really planned. So yeah, basically that's a DSP board. That DIO are OPAL-RT proof. I mean, those IO are compatible with our HIL-IO. So if you want to plug them, just put loop back and everything will work. We approve this board, while some other ECU might need some integration on the signal level. So this is what it is. So the demo setup, we got an OP-4500, which is an HIL simulator, with an OP-8665, which is a DSP, and we're gonna connect both of them together. The first step will be the closing the loop step. Then I'm gonna run a test, and I'm gonna show you all the features to analyze your result. So here you can see my code is running on RTLab. So I got the RTLab running there. And I can put some speed, so something happened there. So you see, I put a speed of 1,000 RPM, so it's running, but there is no gate entering, and because all the gates are active low, I'm shorting my bus, which is not really legal in the real life. And this is why that's cool with the Hill, because it doesn't smoke when it breaks. So I'm gonna put back 0 RPM. Here it is. Okay. And the first step when you integrate a hill chassis is to take your PWM. So here you can see it's digital output here. And the digital output send the PWM. And I'm gonna plug the PWM to output here to my gate signal input on my HIL chassis. Oh, 1 minute. Here we go. So my digital input are here, 0 to 15. That's where I need to plug it. So I plug it. Okay. So you see there, now the DC bus is at the normal value. Before it was like 0. Now it's okay. So what I'm gonna do, I'm gonna check if I receive those gate signals. So that's the first step of the integration. Here is, this is my controller code in Code Composer Studio from TI. So it's a very basic controller. There is nothing really special about it, IDIQ controller. And I got the possibility here to force the duty cycle of my gates. So I'm gonna verify on the other GUI here that I read the right gate. So my digital I/O here. Here it is. So I'm gonna send here, is it running? No, it's not running, this is why. Okay, I run the controller, and here it is. I put 0.5, 0.5, 0.5, and 0. So I see 0, 0.5, 0.5, 0.5. I'm gonna do a sanity check, change the duty cycle for A only, see if I go the result here. So for A up, I see 0.2, and I put 0.2 there. Oh, it's not refreshed. Okay, so 0.2 here, 0.2 there, so I'm happy with that. No, I changed that to 0.9. 0.9 here, 0.9 there, so this gate is well connected. So, same thing here, 0.8. So we see here 0.8 here, 0.8 there, so that's okay. And last check is for the boost. So for the boost, I'm gonna put 0.5. And we see 0.5 here. So everything is well connected. I'm gonna put this one back to 0. Okay, so I connected my gate. Everything is, all my PWM are coming from my ECU and goes to my HAL system. Now, the second thing I need to do is connect my encoder, which will give me my position and will help me to get my IDIQ correct. So my encoder is digital, so I plug from digital input here to digital output there. Here it is. And now I'm gonna, from the hill, I'm gonna force the speed and I'm gonna read it here on my, my DSP viewer. So the speed is 0 so far. I'm gonna put 1000 again. Here it is. So we can see theta electrical is moving around and the speed here is 1000 RPM. So I read the speed correctly. Now for a sanity check, I'll stop the motor running and I gotta check if I see the right theta here versus the theta there. So I got 1031.8 degree, which is it equal to that? I think so, yeah. Yeah, it's equal to the theta I have here. Here it's 0 to 360 and there it's not the same base, so this is why, you know it's cyclic, so. No, because I read the mechanical angle. So for one mechanical turn, I got 4 turn electrical. So this is why it goes over 360 on that side. Most of the time, an encoder will be mechanical, based on the mechanical angle. It's not like a resolver that will be based on the electrical angle. So here I got a nice panel that allow me to change the number of pulse per turn if I need to. Not ECU, not all the ECU got the same number of pulse per turn, so I can change that. I can tune my speed definition, normal, inverse. Sometimes it goes clockwise, sometimes counterclockwise. I can tune my angle offset. There is a lot of very nice feature here to tune your sensor, your angle sensor. So the last step is to close the loop for the current. So I'm going to plug the last cable. Here it is. So for now, I just send a constant 0 everywhere. So I should see 0 amp on that side. Okay, I don't see 0 amp, so I've made something wrong. Okay, maybe I have to check my analog out tab. Here is, all is okay. Okay, I know why. Actually, the motor is running. Okay. I left my duty cycle to very high value and my motor is stopped. So this is why I don't see 0 here. So if I put duty cycle 2.5 everywhere, it should be back to normal. 0.5, here it is. Here. Okay, so I see 0 volts, so everything is well calibrated. I know my gain are okay, so I won't do the check for every channel. Basically, if you do it yourself at your site, you're going to have to check all the channels one by one. But you see, the GUI is made so it's very easy. You just have to pick one signal from the FPGA. So here it's IA, IB, IC, VDC, etc. And you set a gain, offset, depending on your I/O specification, and you run. That's pretty easy to do. Very fast forward. So now I'm going to start to control because everything is well hooked up. So I'm going to start the controller. So for now, I'm just controlling 0. Yeah, for now I'm controlling only 0 ID. 0 ID IQ. So I read ID IQ here is close to 0. Now I'm going to do a step. Where is my ID reference? My IQ reference is here. Well, I'm going to put 100, for example. Is it updated? Okay, I activate the boost, but I haven't activated the source. I'm sorry. Well, I'm going to activate the source now. Okay, so we see here. So I command 100 IQ. So I see on the simulator I have 100 IQ. Now I'm going to spin a little bit to 2000 RPM. So now you see the controller doing its job. And what's really nice is, for example, you're a student and you want to try some control strategies and you don't want to burn a real experiment. You just play with that for hours. I've never coded a controller before. That was my first time. And after 1 week, I got a controller that is stable. I can use the boost, the motor. I can do some control strategy, and I'm not an expert in that. So we democratize the development process of ECU with this kind of tool. It's very efficient to use. So one thing that is really interesting in that tool is you have a FPGA scope that is that sample the data at the FPGA rate. So you can see the event happening at the FPGA level. So here you have the IA, IB, IL, and VDC. So you see IL, there is some oscillation. Maybe I should change my boost control algorithm because of that. And I can change the signal on the fly here. I can pick high C instead, or if I'm going to put back high A. I can change my trigger condition. If I want more resolution, I can zoom in. I can zoom out. It's a really nice tool. Okay, in that tab, I can also open, so I talked about the fault insertion possibility. Here I can open the phase, close it. I don't know how my controller will react to that. I've never tried it. So I'm going to open, for example, the C-low phase. So it looks like it's still stable, but it doesn't like it. Okay. So there is no fault in that controller. It's keep running even if you have a 400 amp on one phase. But basically you can insert fault everywhere you want on the drive or on the boost. I made a mechanical tab. You can see the battery power versus the AC power. So basically that's it. So now there's a time for a question. So you want me to test a strategy? I don't know. Any question? Yep. The time step for the motor is 1 microsecond. So the motor is running FEA modeling approach on FPGA, yep, at 1 micro. And the microcontroller, it's a 100 microsecond, I think. It's like a 10 kilohertz carrier frequency, but that's 100 micro. What I need to say to you is the drive part, not the motor part, is running faster. So you can get the gate event more precisely. What is the drive at? The inverter and the boost on the left side, they run at a faster rate than the motor simulation on the right side. Yeah, it's 250 nanosecond for it. It's faster because you need more accuracy on the gate event that you would need on the AC level after. And there is like a conversion between square waveform and the motor. The motor is feedback is current to the inverter, and the inverter receive the voltage, and the inverter send the voltage. Okay. Yeah, we had to decouple the two solvers. I think I got in the presentation we got a figure about that. Yeah, this one. It's not the same presentation, but you see here, you have like voltage input, and you take the voltage here, you inject it here, and you take the current here and you inject it there. So those two solvers are separated in order to run faster. Yeah? Okay. Let me get that back on the screen. So here, okay. So you can open an IGBT. Yeah, it's on the IGBT actually. You can open it, you can close it, you can short it, you can open it like if it burned. Yeah. Sure. So sometimes it can become unstable, and the control will goes unstable. This is expected actually, and what people want to do with that, you open an IGBT, and your ECU should react accordingly. So it sees the IGBT is open, it should stop firing, it should stop sending gates, and that's what we want to test with those tools. So if there is no more question, I thank you for attending this presentation, and now I'm gonna leave my my partner Imad from NSYS to speak about automated generation of equivalent electrical machine models from finite element analysis for HIL application. So thank you.